I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on angular momentum. In this video, we're going to talk about angular momentum. So what is angular momentum? Well, like linear momentum, angular momentum is the difficulty in stopping a rotating object. So for example, if we have a ball hitting a rod, causing it to rotate, they both stick together and they rotate with the same constant angular velocity. And what we're going to do is we're going to derive an expression for the angular momentum of the ball as it hits the outermost edge of that rotating rod. So can an object moving translationally have an angular momentum? So does the ball rotate after the collision? Well, of course it does because it's stuck to the rod. So we know that it rotates after the collision. And this means that the translationally moving ball has an angular momentum relative to the fixed point. Well, what does that mean? So the ball hits out on the outermost edge, and we want to know how is this possible that a ball can have an angular momentum moving translationally? Well, because the sphere is hitting at the outermost edge of the rod, it's applying a torque which causes the rod to rotate. Remember, it's a force at a distance. So a translationally moving object moving at a distance from a fixed point also can have an angular momentum. So the sphere moving away from the fixed point means that the sphere's translational motion is the angular momentum as well. So the angular momentum can be calculated by simply multiplying the translational momentum by the distance from the fixed point. So we take the mass times velocity times the distance from that fixed point, which is going to be the radius r, and that's going to give us the angular momentum. Now the symbol for angular momentum, that's a capital L. So we can write the subscript L with subscript of particle for the sphere or ball equals m times v times r. So we want to derive an expression for the angular momentum of the rod as it rotates with a constant angular velocity. And for this, we're not going to take into account the sphere. We're just going to look at the rod. So we know that the angular momentum of a particle is m times v times r, and the rod is made up of a bunch of tiny little particles that act at different velocities and different radii. So we're going to sum the individual mass, radii, and velocities to find the rotational inertia of the rod. Well, we also know that the tangential velocity of each particle is just the angular velocity times its individual radii. So we can substitute that in for the individual velocities, and then we can clean this equation up, and we can sum all the values of the individual masses and radii and multiply by the constant angular velocity, and we get the sum of mi ri squared equals omega. Well, we've seen this term, the sum of mi ri squared, before, and that term is the rotational inertia. So we're looking at the rotational inertia of that rod, and we know that we can look at the rotational inertia video that's linked up above if you can't remember the rotational inertias. So the angular momentum of the rod is the rotational inertia of the rod times its angular velocity. Well, that's not just the angular momentum of the rod, that's how you calculate the angular momentum for all rotating objects, is that L equals the rotational inertia of the individual object times its angular velocity. And that is a measure of how difficult it is to stop that rotating object. So this applies for any rotating rigid object, meaning a sphere, a rod, hoop, etc. So let's look at translational momentum versus angular momentum. We know translational momentum is P equals mv, and angular momentum is L equals I omega. And again, that's for rigid objects that are rotating, like a rod, sphere, or hoop. And we know for a particle that it's L equals the translational momentum times the radius. Now for linear momentum, if the net force on a system is equal to zero, then that means there is no change in momentum. So momentum in that situation is a conserved quantity, so momentum is conserved. Likewise, in angular momentum, if the net torque is equal to zero for a system, then that means there's no change in angular momentum for that system. So that means angular momentum is conserved. So like translational momentum, angular momentum is also a conserved quantity. So let's look at an example. So let's consider this man rotating clockwise on a platform holding two dumbbells away from his body. We could calculate his angular momentum if we knew his rotational inertia with the dumbbells and his mass and his arms sticking out, and we knew his angular velocity. But what we know is that that angular momentum is not going to change unless there is an external net torque that is applied. So what happens if he brings his arms in closer and the dumbbells closer to his body? Well, his angular speed increases. Well, why does this happen? So again, there's no net torque, so there's no change in angular momentum. So if we look at the angular momentum equation, L equals I omega, what changed? Well, we had a very large rotational inertia for when the dumbbells are extended away from his body. But when he brings those dumbbells in towards his body, what happens then is that the rotational inertia is going to decrease. And when that decreases, then the angular velocity has to compensate for that. So the angular velocity increases. So in both cases, there's no change in angular momentum. So the rotational inertia decreases, which means that the angular velocity is going to have the opposite effect as they are inversely related to each other. So the angular velocity increases if rotational inertia decreases, and vice versa if there's no net torque that is applied to the system, such as the situation we have with the man rotating. So here's an example of angular momentum conservation in a real world situation. This is a girl that broke the world record on this date, Sophia Lucia. She did 54 pirouettes, but what we want to focus on is the how she orients her body. So you can see she starts with her arms out wide. She brings her arms in a little bit, and you can see that her rotational rate is going to slow down. But watch how she shifts her body to increase her angular speed. So she's going to drop her foot, she'll speed up, and then she's going to lift her arms over her head, making her rotational inertia decrease, and you can see her angular velocity increases until she can't decrease her rotational inertia anymore. So eventually friction causes her to slow to a stop. Let's look at an example problem. Disc is rotating around the center with a coin on it, and as the disc spins, the coin slides further from the center. So if the coin's mass is significant and compared to the disc, but not necessarily equal, what's going to happen to the rotational rate of the disc as the coin slides outward? So if we consider the coin disc system, as the coin slides outwards, it increases the radius of rotation for the coin. So we know that in this situation, there's no external torque because it's just a coin and a disc sliding together. So that means the angular momentum is conserved. So the initial situation is going to equal the final situation. We can substitute those equations in, that I omega equals, for the first situation, equals rotational inertia times the angular velocity. So what changes from situation one to situation two? Well, the coin sliding further away, that means the rotational inertia increased for the whole system, which means that the angular velocity is going to decrease. Again, those are inversely related. So that means that the rotational inertia increases from the first to second situation, which means that the disk would actually slow down. So let's look at the second example. So we've got a ball with mass m moving with an initial velocity. You can see the initial conditions there. We have it hitting a rod and sticking and rotating. And what we want to do is we want to derive an expression for the final angular velocity of the rod mass system. So because we have a collision occurring, we're going to draw angular momentum bar charts. So let's look at the situation. The ball strikes the rod, which means that it's hitting at a point away from its axis of rotation. So that means the ball has an initial angular momentum. So the ball has all of the angular momentum. When they collide and stick together, that gives us that the ball and rod rotate together. So that initial angular momentum is going to equal the final angular momentum. So using the bar chart, we can write our conservation equation. We know that the initial angular momentum equals the final. We can substitute the equation. We can use the ball as a particle, so that's m times v times r. And then we can use the I omega for the angular momentum of the second situation. And then we can solve for the angular velocity, which is mvr divided by the rotational inertia. But those are not all the symbols that we're allowed to use. The symbols that we're allowed to use are just the mass and length of the rod and mass, velocity, and radius of the ball. So we know that the rotational inertia is just going to be the sum of the rotational inertia of the rod and the ball. So we can write that as IB plus IR, and R is the value of the length of the numerator. That is the length of the rod, which we defined as capital R. So we're going to change that to MV capital R. So the rotational inertia of the ball is mr squared, and the rotational of the rod is 1/3 mr squared because it's rotating around its end. And we can add those together and put that in the denominator. And then we can factor out the r squared term. And we have an r on the top and 2 on the bottom, so one of them cancels out in the bottom. And this gives us our expression for our angular velocity with the symbols that we're allowed to use. Now, don't do bad algebra and cancel out the m's on top and bottom because the plus sign does not allow you to cancel that because the lowercase m is not in the 1/3 capital M. So let's look at a third example problem where we have the same rotating rod, two identical rods now. One collides and sticks together like we saw in the previous example. But in this situation, that the ball bounces off and rotates angularly the rod. And we want to know which situation gives the rod a larger angular momentum. So we can see that the ball collides and sticks. We draw our momentum bar chart. It's going to be similar to the one that we drew previously, where the ball has all the angular momentum to start and the rod ball stuck together give us the equal momentum. Now in the bounce situation, again, the ball has the same angular momentum as it had before with the same mass and same velocity, but now the ball is going to bounce off and move in the negative direction, causing the rod to go in the positive direction. Well, if we take that +4 minus plus the -1, that's going to give us 3. So if we compare the system 1 to system 2, the stick situation versus the bounce, and what we're looking at is just comparing the rod's angular momentum. So we can see that the rod in the final situation for system 2 has a larger angular momentum than in system 1. Well, larger angular momentum, each rod was identical, so it has the same rotational inertia. That means that the angular velocity of rod in the second situation is going to be larger than the first. All right, we're going to look at a similar situation, except it's going to change it up just a little bit. So we're going to not change the system one, the rod's going to rotate, but in this case, we're going to have the rod rotate and stick with the ball hitting at the midpoint. So which system, if either, gives the rod a larger angular velocity? Well, again, we're going to look at a momentum bar chart. We've already drawn this momentum bar chart. We have the ball with an initial angular momentum and the ball and rod stuck together at the outer edge. The midpoint, well, because the ball's moving closer, it's not going to have as much angular momentum. MVR is going to be a smaller value. So that means the rod and ball rotating together are going to have a smaller value. So we compare those two and we can see, well, the ball having a smaller initial angular momentum means that the rod and ball are going to have a smaller angular momentum in the final situation, which means that system 2 is going to have a smaller angular velocity. Now also we can look at the ball moving at the same speed, coming to a stop and sticking together is going to apply a force to the outer edge or the midpoint, which means that that force is going to cause a torque. Well, the torque is going to be smaller when the distance the force is applied is smaller, so the midpoint's going to apply a lesser torque, which means if there's a lesser torque, there's a lesser angular acceleration. Lesser angular acceleration means a smaller angular velocity. So this leaves us with one final question that we are going to ask. In the situation that we've seen a couple times where the ball collides, sticks, and causes the rod to rotate, during that collision, is translational momentum conserved as well? So we got to ask a follow-up question. Is there an outside force that doesn't allow the objects to move? Well, there is an outside force. The pin is holding the rod in place and not allowing it to rotate. So because the pin doesn't allow the rod to rotate, that means that translational momentum is not conserved because there is an outside force. If there wasn't an outside force, then the whole rod would just slide instead of rotating. So this was an introduction to angular momentum. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below and subscribe to my channel, Happy Coaches, and follow me on Instagram and Twitter at Happy Coaches.